So difference between voltage and current. Voltage is the pressure, motivates the flow. Voltage is measured across two different points in the circuit versus current is the flow of electrons. You measure that through a single point. Okay? Thumbs up when you have an answer. For the sake of time, correct answer is A. Voltage causes current. Okay, it's the push, it's the pressure. You figure out how much current by voltage divided by resistance. But voltage is the motivator. Current is the result. Okay. So in this question, I'm kind of teaching slash introducing to new terms. Voltage drop or potential drop has to do with energy. You're using energy across a voltage drop. Like where are we converting electric potential energy into a different type of energy? Like what part of the circuit is using, or like, I don't know if consuming is the right word, but using that electric potential energy and converting it to different types of energy that we're using for other purposes. Thumbs up when you got an answer. The biggest consumer is the light bulb. We're converting that electric potential energy to heat and light. Okay. The wires have a little bit versus a potential gain or a voltage gain is part of the circuit that gives energy to the electrons, gives electric potential energy. So that would have to be the battery. Anything that's the power supply is giving energy to the electrons. Okay. So we look at this as a complete loop. When we say from here to here, giving energy. Okay. Thumbs up when you have a guess. Okay, I'm just going to straight up tell you this one because you're just guessing. Might be good guesses, but correct answer is D. They're same at all points. Okay. Here's an analogy that, or a parallel measurement. Current in a river. Assume the river doesn't have any tributaries coming in, or no places like sinkholes, drainage, whatever. So at any point in the river, so current is measured in cubic feet per second. How much water, the volume of water going by a certain point, one point, like every second here. And then you can look at it another spot. If these two measurements along this river were different, if this was more than this and is flowing this way, you'd have like a dry space. If there's more water leaving than was coming in. Does that make sense? And if there's more water coming in than leaving, you're flooding. Does that make sense? So on a normal river, like 99% of the time, the current at every spot is identical to every other spot. You have the same amount of current, same amount of water flowing by a certain point here as you do over here. Okay. Now, if you've ever been canoeing or tubing or just floating, doing a float trip, you know, some parts of the river or creek move faster than others. But does that mean the current is more? What part of the rivers, like how would you describe the riverbed when the water's moving fast? Okay, it could be steeper. That's true. Narrower, shallower. Okay. So more water, sorry, you have to have a lot of water get through a narrow spot, narrow or shallow spot, so it's moving faster to get that same amount of water by that spot versus somewhere that's wide and deep. It's slow moving, but has the same current. Does that make sense? Same thing here. Anywhere along here, this would be like the rapid part. Shallow, steep, narrow, okay, but has the same amount of current at every spot. Good with that? Correct answer is just C. Okay, just C. Um, they actually go faster. This is like the narrow part. It's kind of like putting your thumb over the edge of a hose, into the hose, and like squirting it. Okay, they're moving faster. Um, the energies that use not they're not eaten. Okay. All right. So resistance. Um, characteristics that give resistance. So the material that an object is made out of has a lot to do with resistance. So like, is it a conductor? Is it an insulator? Is like, what is that? So that's the resistivity of the material. Each material has a certain amount, but the geometry, the shape of the material electricity is passing through also makes a difference. What do you think would have, so resistance is caused by, um, part of it is remember the thing, like where the electrons going through and getting beat up by like the gauntlet of protons. Okay, so that's where a lot of resistance comes from, is that gauntlet. Okay, which do you think would have more resistance? Sorry, less resistance, a short wire or a long wire? Short. Is everybody okay with that? Like if you had to have an extension cord, and a short one and a long one would both be able to plug in the thing you're trying to plug in, which one should you use? Nope. You want to use the short. Okay, it has less resistance. Okay, good with that. Now, which do you think has less resistance, a thick diameter wire or a thin diameter wire? Here's an analogy. Which is going to allow more water molecules to get by a certain point every second? A garden hose or a fire hose? Fire hose. Why? Has a bigger diameter. Okay. There's less resistance. It's kind of like having a 5-lane highway versus like a 2-lane road. Okay. So a thicker wire has less resistance. When you go shopping for wire at a hardware store, they're going to rate the wire based on gauge, like an 18 gauge wire, 12 gauge wire. Okay. The lower the gauge, the thicker the diameter. Okay. Think of it this way. The lower the gauge, the less the resistance. So when you own your own house, you got to do some wiring, give you a little insight into what you're shopping for. Okay. Oh, last one, hot wire versus cold wire. Which one's going to have less resistance? A lot of people say hot wire has less resistance because things are hot. They're able to flow better, like move more. That's true, but that also impacts the vibrations of the protons. So as it gets hotter, the vibrations of the protons are going more, and so the gauntlet's more violent. So actually, a hot wire has more resistance. A cold wire has less resistance. This is why you have a cooling fan on your computer. This is why hardcore gamers have a cooling system for like to help speed up their processor and all that stuff. Okay, good with that. So a short, thick, cold wire, least resistant. Talk to your neighbor. Correct answer is B, the skinny filament. This gets, um, yeah, hot enough to glow white hot. Do what? Right, and it's in a vacuuming, that's why the glass bulb's there. Keep oxygen out of it. Tell your neighbor. So we good with A? Hotter the wire, the more resistance. Okay, so this comes up often, like this question. So I thought I'd just throw it in the PowerPoint slide. Have you ever noticed that your car has a hard time starting on colder mornings? Or if you've ever left your cell phone in your car outside overnight on a cold night, probably never happened. But random chance that it has, and you go to turn it on when it's cold, it's a struggle. It's like, and so the follow-up question is like, well, I thought it was less resistance when it was cold. Like, why is it struggling to start? What does your car have? What does your cell phone have? What is the the initial power source, a battery. A battery runs off of chemical reactions. And so what happens to the rate of reaction when it gets colder temperatures? It gets less, like it slows down. And so it struggles to produce the electrons needed. So anything battery operated in colder temperatures is going to struggle. That's not resistance, that's just chemical rate of reaction. Good with that? Thumbs up when you have a guess. Okay, correct answer is only C. This is talking about current. This is talking about power, which you'll learn about tonight. So one side compared to the other, the two prongs, there's a difference in electric potential from one side to the next. One is crowded, the other one is not. Okay, good with that? Okay, voltage is not flow, it pushes. Correct answer is B. Okay, so the Van der Graaf generator had a lot of voltage, okay, but not much charge. What will kill you is the current. Current is what kills. Okay, just to give you some idea of like how much 1 milliamp, you can feel it if that flows through your body. 5 milliamps, it hurts. 10 milliamps, you got muscle spasms. 15, you're in like seizures. 70 milliamps, if that goes through your heart for more than a second, you're dead. Okay. When I was in college, one of my roommates was a physical therapist, and he brought home one of those stimulating shocker things for your muscles. And so we had a lot of fun with that. Like we hooked it up across my quad, like cranked it to 10. It was like, "Ah!" But it was like crazy art. Like you could see that muscle just so defined. It was hurt like crazy, but it was really cool. So somebody else asked, like, what about defibrillators? The ready, clear. Okay, that is not a steady, like not a current. That's more like a static shock. Okay, so there's just like the surge of electrons trying to jumpstart your heart. Okay, it's not like a. It's just a boom. Does that make sense? The difference there. There's definitely a lot of electrons going through there, but it's not steady. Good with that? Thumbs up when you have a guess. Correct answer is E. All three of these. The whole point when you get shocked in this scenario is if the bird's feet have an electric potential difference. If there's a difference in electric potential from one foot to the other foot, the bird's toast. Okay, so if the bird somehow is able to straddle from the wire to the ground, there is a high electric potential difference from the wire to the ground, and the electrons are super motivated, like, like that's why you never touch a downed electric wire, because you'll provide a path to ground. Okay, the bird's grabbing one wire. There is no difference of electric potential from this foot to this foot. So there's no reason why the current would want to go through the bird's body. Okay, and if somehow the bird could straddle another wire, that would be bad too, because there would be a difference in electric potential. Okay, good with that? It's the difference that makes all the difference. Okay, so the prong, safety prong on and plug in. This is a ground wire. Your device will work with or without this thing. Okay, it's completely a safety device. So let's pretend we didn't have the ground wire. Washing machine, let's say, has an off-center load, shakes, and in the shaking, somehow that wire becomes frayed. And then the copper inside of that wire touches the metal casing of the washing machine. Okay. And so when you go to do laundry, then all of a sudden it's like you become a path to ground and you get shocked. Okay. The ground wire prevents this by this ground wire actually is physically bolted or screwed to the frame of the washing machine. Okay. And then this goes to ground, like to the plumbing. So if the wire frays and touches, the path to ground goes that way. You trip a circuit breaker repeatedly, but you know something's going on, and then it doesn't go to you. Good with that? I'll give you a hint on this one. The voltage is determined solely by the power supply. The voltage is determined solely by the power supply. Thumbs up when you have a guess. Have a conversation.
Like when you keep this thing, I'm pretty sure you turn the resistance down because that strong current. Voltage divided by resistance equals current.
Correct answer is?
B.
Correct answer is B. You're still hooked up to 120 volts. That stays the same. Okay. You get brighter, you need more current. In order for more current, you need less resistance. Good with that? Correct answer is okay. So here, this is just, we did this yesterday. This is what I said don't do. Okay, this is just 1.5 volts. The voltage isn't very high, but it gets hot because the current is high. What would cause the current to be high? Okay. A low resistance. Okay, the wire itself does not provide that much resistance. This is known as a short circuit. Have you ever heard of that phrase? Like, oh, it got short circuited. It means it's a circuit that's complete, but it doesn't have a major resistor. Does that make sense? So you have a lot of current and that fries stuff. Okay. Give you a hint. The answer is E. Tell your neighbor what the correct answer is. Okay, correct answer is voltage stays the same. It's the same power supply, same battery. There's more resistance now that the light bulb is included. Current goes down. Okay. So when I was a kid, I helped my dad jump start cars, and I'd look at this and I'm like, oh, this is crazy. Like holding bare metal, I'm like, man, this, and I touch them together and it's like, oh, I'm like, what's going on? I'm like, what would happen if I like, just kidding. Nothing happens. So why, what, I mean, they're still on. Does anybody know the voltage of a car battery? 12 volts. Okay. This is a short circuit when I'm doing this. Like there's very little resistance. Okay. And there's enough current to actually spot weld these two together if I left them. But my head is providing too much resistance for any substantial amount of current to go through. Okay. Now, my skin is more resistive, whatever. There was a guy on Darwin Awards who killed himself with a 9-volt battery, hooked to like metal probe, stuck it through his thumb. The current went through his blood supply, which is pretty ionized, good conductor, through his heart, dead. So don't do that. Like if I hooked that to my tongue, that'd probably hurt. I don't really want to do that. But good with that. Okay. So we hit that. Quick. You got to know how to jump start your car. That's just a good practical knowledge to have. Okay, so let's say you've got your dead battery. Okay. And you got your good battery. So if someone pulls up, okay. So positive usually indicated with red, and black's usually indicated, or negatives with black. There's nothing special about the colors. Like the wire's the same. It's just copper. It's just a way to keep things straight so you don't cross things over. So what you're going to do is you're going to take the dead battery, hook it up to the positive. And then you're going to hook up your positive to your good and your red to your black negative. And then lastly, what you're going to do is the safest way to do it is to hook it to the frame of your car, like the metal frame of your car. Super low chance of this happening, but it is possible. There's hydrogen gas produced in your batteries. And when you make this last connection, a spark can happen, and there's a slight chance that you'd ignite that hydrogen gas. So what they say is your last connection, do it away from the battery. Do it. The black goes on the metal frame because this is connected. This is considered ground. Like somewhere along here, this is connected to the wire frame, and that completes the circuit. So what you're going to do once you connect it, rev the good engine a while because there's this thing called an alternator that charges the good battery. Okay. Then try to start it. If it doesn't start still, let it run for a while. Let the good car's alternator charge this battery. And then rev it up, try to start it. Once it starts, just disconnect it in the same order you connected it, like the opposite order you connected it. And do not turn this off for like 20 minutes or so. Let your alternator charge this dead battery. Don't just drive it home 2 minutes and turn it off. You're going to have to jump start it again. That makes sense? Like, let it charge up. So you got a pre-quiz tonight. Whew, we made it.